Welcome back. In this video, we're going to look at some examples using the empirical rule. And actually, right before we do that, I forgot to mention one more thing. So we talked about in the last video, right, how 68% of our data is one standard deviation above and below our mean, right, representing by this purple portion of our graph. 95% is 2 standard deviations below the mean and above, right? From 2 standard deviations above to 2 standard deviations below, right? And then 99.7% is 3 below to 3 above. But because our normal distributions are also symmetric, that means if you cut it down the middle, the same amount of data, right, is on the left-hand side and the right-hand side. So with this symmetry property, we can say, well, 50% of our data is on the left and 50% is on the right. Okay, great. So we can take that even a step further and apply the symmetry rule to these rules down here. So if there's 68% of our data total between 1 standard deviation above and 1 standard deviation below, we'll cut that 68% in half. And what you really have is 34% of your data here between the mean and only 1 standard deviation above your data. And likewise, the other half of that 68%, this 34%, is between the mean and 1 standard deviation below. Great, so then let's cut our 95% in half. 95% divided by 2 is 47.5%. So if we have 95% from here to here, 2 standard deviations above to 2 standard deviations below, then what we really have is 47.5% from our mean, right, cutting it in half to 2 standard deviations below, and the other 47.5% from the mean to 2 standard deviations above. Well, we've already filled in 34% and 34%, right, from 1 standard deviation above and below from the mean. So if we take our 47.5%, subtract the 34%, then we get this 13.5%. So we can say from the first standard deviation to the second standard deviation below the mean, there's exactly 13.5% of our data. Likewise, from the first standard deviation above to the second standard deviation above, in between that region, there is 13.5% of our data likewise. We can use the same idea, right, to fill out the distance between the second standard deviation to the third standard deviation and get that there's 2.35% of our data in this section. And just note that, remember, this is 99.7%. So what does that mean we have left? Let me try this annotating. Well, if 100% is under the entire curve, we subtract 99.7%, we're left with 0.3%. And then we divide this 0.3% by 2, right? Because it's half of it, again, will be on this side. The other half will be on this side. So if you divide 0.3 by 2, you will get I believe it's 0.15. Let's see. I don't think it's 0.015. So Yep, so this would equal, yeah, so it's 0.15% on each side, right? So and this little bit here is 0.15%. And over here on this side is also 0.15%. And we'll see at this 0.15% will come into some questions in the next slide, okay? So let's see. All right, so let's see if I can clear all my drawings. Okay, so I've kept our chart here to make life a little easier for us. So we have a question here. It says the lifespan of gorillas in a particular zoo are normally distributed. Okay, so we know that the lifespan of gorillas are normally distributed. That's great. We know what the distribution looks like. They give us the average age of the gorilla, which is 20.8, and the standard deviation of 3.1. And they want us to use the empirical rule to estimate the probability of a gorilla living less than 23.9 years. So, to solve this problem, what I recommend doing first is to draw your distribution. And I know this looks really bad. We can draw a little dotted line. This will be our mean, right? The mean is at the center of every normal distribution, right? So for this particular normal distribution of gorilla lifespans in this zoo, we're given that the average or the mean is 20.8, right? So that goes in at the center of our distribution. We're also given the standard deviation, which is 3.7, right? So if I draw this line will represent our first standard deviation. What do I need to do? I need to add 3.1 to this 20.8, right? The standard deviation is 3.1. So it's 3.1 units or years, right, away from our mean of 20.8. So this is 23.9. And then I know this isn't really to scale, but I'll go 2 standard deviations out, right? So this is 1 plus 1 standard deviation. This is plus 2 standard deviations. So now I'll add another 3.1, right? So 23.9 plus 3.1 is 27. And then again, I know I didn't really draw this very well. This is plus 3 standard deviations. So if I add 3.1 to 27, then I know 30.1 years is 3 standard deviations above the mean, right? Now we can do this. This is minus 1. It's supposed to be a negative. Minus 1 standard deviation. So now what do I do? Well, now I need to go 3.1 units to the left, 3.1 years to the left of our average, which is 20.8. So if I do 20.8 subtract 3.1, I get 17.7. I can do this again, right? This is 2 standard deviations below the mean. If I subtract 3.1 from 17.7, I'll get 14.6. And then lastly, -3 standard deviations below our mean. Just subtract 3.1 again, and I'll get 11.5. Okay, so we've drawn our distribution. And now we can answer the question with the help of our kind of our cheat sheet over here. So the question, it wants to know, by using the empirical rule, estimate the probability of a gorilla living less than 23.9 years. So if we know the distribution of all of the gorillas' lifespans, if we find the area under the curve, right, then that will tell us the percentage of all gorillas that will live less than 23.9. So if we use our 23.9 as our cutoff, we find the area under the curve to the left of 23.9, right? Because it's the probability of a gorilla living less than 23.9 years. So we want all the ages to less than 23.9, which is everything to the left of our cutoff. Let's see if I can change this color to kind of help. Great. So here's 23.9, right? This is the number we're asked about specifically. Estimate the probability that a single gorilla lives less than 23.9 years. So what we need to find is the area under this normal distribution curve, right? Everything here in red to the left of 23.9. And again, it's to the left of 23.9 because it wants to know the probability of a gorilla living less than 23.9 years, right? So everything less than 23.9 is to the left of that cutoff value. So how can we find this area under the curve? Well, 23.9 is exactly one standard deviation above our mean. And we know all the percentages of our population specifically, right? That will be under the pieces of this curve, right? So all we have to do is add these percentages over here that we've also marked on our distribution over here, right? So we've gone one standard deviation above the mean. So this piece is 34%. Now if we take this piece, right, this is one standard deviation below the mean, right, from our mean to one standard deviation below. That's another 34%. Put a plus sign there. And then if we go from one standard deviation below to two standard deviations below, we know that's 13.5%. And then if we go from two standard deviations below to three, we know that that is 2.35. I'm going to stop doing the percentages, but just know that is still a percent. And then don't forget about this last little piece from our last slide. We know that this contains an extra 0.15%, right? This is still in our red shaded area, right? Everything to the left also contains that 0.15%, right? So if we add all of this up, it will give us our answer. And I get lost my mouse somehow. Can't see it anymore. I get 84% for this final answer. Okay. All right, so now I will clear this for our next question. Actually, I'm going to try to simply erase, reuse my same drawing. Okay, so now we're given a different normal distribution, right? Now we're talking about lifespan of meerkats in a particular zoo. Maybe it's the same zoo. Maybe it's a different zoo. Doesn't really matter. We're given that they are normally distributed as well. Oops. Let's see if I can undo that. But these meerkats, they have an average lifespan of 13.1 years with a standard deviation of 1 years, which makes sense, right? Meerkats probably live different lengths than gorillas do. So now to fill out this bell curve, right, this normal distribution with the information that we're given, we're going to put 13.1 at our center, right? That is our mean or our average. And these meerkats have a standard deviation lifespan of 1.5 years instead of 3.1. So now from our mean of 13.1, I'll add 1.5, right? Because that is our standard deviation now. So 1.5 plus 13.1 gives us 14.6. If you add 1.5 to 14.6, we get 16.1. And then if we add 1.5 to 16.1, we get 17.6, and so on. We subtract 1.5 from our 13.1, we should get 11.6. We subtract another 1.5 from this 11.6, we get 10.1. And then if we subtract 1.5 from this 10.1, we would get 8.6. Okay, so we filled out what our distribution looks like for meerkat lifespans. And now the question wants us to estimate the probability of a single meerkat living longer than or greater than 14.6 years. Okay, so let's find 14.6. So 14.6, just like our last example, it also happens to be one standard deviation above our mean. But this time it wants to know the probability of any of the meerkats living longer than, right, or greater than 14.6 years. So now what do we want? Now we want the area under the curve to the right of 14.6. And again, to find this, we can use our cheat sheet, right? So in between one standard deviation to two standard deviations above the curve, this is 1, and from 1 to 2, we know there's 13.5% of our data under the curve here. And then from 2 standard deviations to 3 standard deviations under the curve, in between 2 and 3. We know there is 2.35%. And then don't forget from our last slide, we know there's still 0.15% beyond 3 standard deviations, right, above the curve. So now all we have to do is add these together and we'll get 16%. One way I did that so quickly was that if you remember from the last problem, we found this green shaded area. We found, oops, a little too much. We found, uh-oh, it's not what I want to do. Sorry, getting used to this. We found the area under the curve to the left of 1 standard deviation above our mean. It was a different number here, right? It was something in the 20s, maybe 30 even. But the area under the curve we found was from 1 standard deviation above the mean to the left, right? All the way to the left. And so from our last problem, we found this area under the curve was equal to 84%, right? This time we're finding the exact piece that we didn't find last time. Remember, 100% of our data has to be under the bell curve or the normal distribution total. And this is true for any normal distribution, right? So it doesn't matter that we're talking about a normal distribution here. So to find this answer, after we drew our picture and realized the number it was asking for was 1 standard deviation above our mean, we could have taken 100%, subtract the 84% we found to equal the 16%. But this way works as well. Adding this gets you the same exact answer, which makes sense. It's all got to add to 100%. Okay. Seems like my mouse sometimes disappears. Okay. All right. All righty. I think this will be our last question. So let me see if I can move this over slightly so I have more room to draw. All right. So let's draw our bell curve. Sorry, not a very good artist. Okay, so this time we're given that lifespans of meerkats again in a particular zoo are also normally distributed. This is a different zoo, or it's a different population of meerkats, right? Because now our average lifespan is 10.4 and our standard deviation is 1.9. So now at the center of our graph, we'll put 10.4. If I go 1 standard deviation above the mean, I'll add 1.9 and I will get 12.3. If I go 2 standard deviations above the mean, I'll add another 1.9 and we'll get 14.2. Sorry, this is getting a little crowded. We add 1.9 to 14.2 to get 3 standard deviations above. This would be 16.1 up here. We can do the same thing. If we go 1 standard deviation down from our mean, believe we subtract 1.9 from 10.4, that should give us 8.5. Yep. Yeah. Sorry, it seems like my mouse likes to disappear on me, which is not good. All right, so if we subtract another 1.9 from this, we would get 6.6. And if we subtract 1.9 one more time, should get 4.7. Okay. So let's estimate the probability that a meerkat lives less than 16.1 years. So we're looking for the area under the curve of just about everything, right? If 16.1 is 3 standard deviations above, and we want the area under the curve to the left, and we know we need the area under the curve to the left because it wants the probability that a meerkat lives less than 16.1 years. How can we solve this? Well, what do we know that's above 16.1? We know above 16.1, greater than 16.1 gives us that 0.15%, right? And just like in the last example, we know 100% is everything. Let's just take 100%, subtract it from the 0.15% we know we're missing. And what do we get? We get 99.85%. A little bit easier than adding up 2.35 plus 13.5 plus 34 plus 34 and so on. But if you felt more comfortable with it, you could do it that way. Okay. And so lastly, looks like we're given an approximately normal distribution with a mean of 159 and a standard deviation of 70. Excuse me. So let's now fill that normal distribution in. It'll look the same, right? So now we've got a mean of 159 and a standard deviation of 70. So if we add 70 to 159, we'd get 229. We add 70 to 229, we get 299. And if we add 70 more to 299, we'd get 369. Now, if we subtract 70, we get 89. Subtract 70 from 89, you get 19. And then if you subtract 70 from 19, you get negative 69. So our first question is, what percent of values are within the interval 19 to 159? So this is the first time we haven't seen just a less than or greater than, right? Now it wants to know the percent of values within 19 to 159, which is fine, right? We can answer this well as well. Here's 19. Here's 159. That's just our mean, right? So it wants us to find the area under this section of our curve, right? From the mean to 2 standard deviations below. So we know this section, right, from the mean to 1 standard deviation below has 34% of our data. And we know this section, right, from 1 standard deviation below to 2 standard deviations below has 13.5%. So if we add those two together, we get 47.5%. Okay, so this is 47.5. Okay, now it's asking us almost the kind of inverse, right, of this question. It says, what interval contains 99.7% of all values? Well, if we go back to our cheat sheet, right, a part of this rule is that 99.7% of your data lie 3 standard deviations above to 3 standard deviations below. So we know 99.7% of our data will fall 3 standard deviations below to 3 standard deviations above. And because we've drawn out our distribution, right, and added 3 standard deviations, subtracted 3 standard deviations from the mean, we know 3 standard deviations below is our negative 69, and 3 standard deviations above is 369. So the interval that contains 99.7% of our data is negative 69 to positive 369. And you can write parentheses there if you want to show that it's a interval. Okay, so now it wants to know what percent of values are outside of the interval 19 to 229. All right, so the percent of values outside of 19 to 229 would be in this green shaded area. Here's 229, so outside of 229 would be everything above 229. And we could do this, right? We could calculate the percentage here from 2 standard deviations to 3 standard deviations. That's 2.35. We know there's 0.15% here. And then from only 1 standard deviation to 2 standard deviations here, this would be 13.5, right? This would be another 2.35 plus 13.5 plus that 2.35 plus, don't forget about this guy here, our last little 0.15%. So we could add all of this up, right? Or what we could do is we could first find the percent of values inside of 19 to 229 if we wanted to. So I'll stick with my red color so we could find this interval here and subtract that from 100. Because again, if 100 is everything, we subtract what we find on the inside from 100, all we're left with is our green shaded area, which is what we're looking for. We already found that these two pieces make 47.5%. So if we add this piece right here from the mean to one standard deviation above, that would be 34%. This would give us 81.5%, right? And then 100 minus our 81.5 would give us 18.5%. All right, these are percentages as well. So let's add this up and see if we get the same thing. It should be, so if we add 2.35 plus 0.15 plus 13.5 plus 2.35 plus 0.15, adding all of that up. Sorry, my mouse disappeared on me again. Adding all of that up, I get the same exact thing, 18.5%. So all that just to say there's more than one way sometimes to solve these problems. Just depends on how you want to think about it and what seems easiest to you.